Yeah, so ladies and gentlemen, let's begin our lecture 11 on computer vision. I'm honored to welcome Professor Francois Rameau. He's adjunct research scientist at NAMI and assistant professor at Sunny Korea. Let's give a big round of applause, ladies and gentlemen.
Okay, good morning, everybody. So thank you very much for the very kind introduction. And thank you very much for being here today after this tough hike you had yesterday. How was it? It was nice? Yeah? Okay, I'm sorry I didn't join this year, but I promise next time I come, I will work with you guys. So today I would like to discuss about a quite exciting topic at the time, I think something relatively trendy. This is the problem of deep learning-based 3D mapping. Okay, so I hope you will all find it interesting. I will try, this is maybe a bit ambitious. I will try to cover actually some of the latest development in that field. But before digging into the technical and scientific details of that field, I have to, I think, to introduce a bit like where I'm currently working, because, well, that's actually a quite peculiar place. I work for the State University of New York, but in Korea, okay, which is a kind of weird situation. So Sunny Korea is basically an extended campus of two of the flagship universities of the SUNY ecosystem, which are Stony Brook University and the FIT, which is the #1 actually design and fashion school in the world. And so you can see that I'm not a very fashionable person. You know, I look like a 20 ohms resistor today. So, but yeah, so I don't belong to FIT. I am actually part of the Stony Brook University. And interestingly, I have 3 affiliations. I have one in NAMI, as it was mentioned before. I am assistant professor in Korea, and I'm research professor in the US. So yeah, I'm on multiple continents somehow. And as I mentioned before, we are an extended campus. So basically, our students, they spend like at least 1 year of their courses in the US, in Stony Brook, Long Island, okay? And the rest of the time, they're studying with us. So this is the same curriculum exactly than in the US, and they, in the end, receive like an American diploma, as if they were actually just studying in the US. So we are really just an American university, but on the Korean soil somehow. So that's something quite interesting, but we're cheaper, okay, don't say that. But so after this short advertisement, I want, because we have so much things to talk about today, I will jump directly into the core of that topic, which is 3D reconstruction. And I believe that pretty much all of you in this room has some intuitive like conception of what 3D reconstruction might be, but nonetheless, we'll start with some, I will call it semi-formal definition. That's my definition of it. So 3D reconstruction, essentially, this is how you create a 3D representation of an object or a scene from data you will collect from various sensors, okay? So you can see that in this video, it's like this person is captured by tens of cameras surrounding her from different viewpoints. And what we want to do is to basically reconstruct the structure of that person in 3D, in the 3D space. Okay, so you start from 2D images and you want to lift it up to the 3D space. But of course, like, so I am a bit biased, you know, like for me, cameras is the best sensor ever because I'm a computer vision person. So the example you have seen before is a reconstruction based on camera, and this is indeed a sensor that is, I think, quite desirable for that task because it has a certain number of advantages. This is compact, this is energy efficient, this is affordable. So, you know, I think you have all seen that nowadays camera, they're very everywhere. They're in your car, they're in your smartphone and everything. But you can do 3D reconstruction with plenty different kind of sensor as well. So do you know any sensors actually you can use to make 3D reconstruction? LiDAR is a good one, for instance, and there are plenty more, right? Like instead of using one camera, maybe you want to use like a camera rig like this. So you just like use multiple cameras, and then it will give you certain advantages. You will have directly the 3D metric scale reconstruction. So, you know, for certain application like estimating the displacement of a car, that will be a great thing. But also this is a bit more painful to use because now you need to calibrate this system. You need to synchronize it, so it makes it a bit more bulky, a bit more complicated. And as you rightfully mentioned, LiDAR is a great one. And, you know, like, you directly get the 3D structure of the scene, like, from a single shot, okay? But LiDAR doesn't give you plenty of information. This is much sparser than an image. You miss a lot of semantics of the scene, etc. This is not a sensor I use a lot, actually, but this is a very interesting one nonetheless. And there are plenty more, right, like depth sensors, etc. We can mention about like radar. So many things. You can be creative. You can even make like, I don't know, 3D reconstruction from a thermal camera if you have a specific application in mind. But today we'll focus exclusively on camera-based 3D reconstruction, okay? So you might also wonder, like, is it really needed to do some 3D reconstruction of something? So do you have actually any idea of business in mind in like for instance, 2 days ago, we were talking about like the commercialization of AI and, you know, business idea. Do you have any business idea where we can apply 3D reconstruction? In video games, for instance, that could be a thing. Like, for instance, we can reconstruct that room and put some players, you know, you can have a sort of Counter-Strike, you know, in that room. That can be one application. And there are plenty more, right? Like, personally, I like to try to resolve problems related to autonomous driving and robotics. I have actually a very good friend of mine is working in civil engineering, so he's reconstructing bridges and in 3D, and he's trying to detect like some defect inside of this 3D reconstruction, like is the bridge gonna collapse, basically. Like AR, VR is a big thing. Like, you know that Meta invested so much in the past like 5 years at least in those kind of technologies, and there are many, many more. And I think that there is actually a great future for those kind of technology, and this is likely that it's gonna be deployed at very large scale in the near future, okay? So I know that some people in this room, for instance, were working on cultural heritage using 3D reconstruction, but well, actually, I'm sure you can be creative and find new ideas of business that involves 3D reconstruction. And now the $1 million question is like, how we do that actually? And this is what we're gonna discover in that short lecture, okay? And especially I want to put an emphasis on the deep learning-based 3D reconstruction, at least the recent one that came out and somehow completely transformed the field of 3D vision. So like in the past 5 years, I would say that we don't do 3D vision the same fashion we're doing before. Everything is changing extremely fast, okay? And thanks to like, well, as you know, like the development of new strategies in deep learning and neural network. Okay, so I identify basically two emerging or like recent, like kind of family of strategies to do 3D reconstruction of the scene, and we will try to explore both of them. One of them is a per scene reconstruction. So basically you first collect all your images of that scene, and you will basically try to fit a network somehow. You will try to reconstruct that scene from this set of image by fitting the scene with like either a network or we'll see actually some other fashion. So one of those techniques is NERF, which is a raycasting technique that we'll discuss. And there is also a more recent one, which is a rasterized approach called Gaussian splatting. And there is also a new kind of approach that are actually expanding very quickly these days. They are the direct feed-forward models. They are just huge neural networks, and you give them the image, and in a single shot, they're gonna make the reconstruction of your scene. And it sounds a bit magical, and it is actually. And those approaches tend to be actually more and more competitive compared to more traditional kind of 3D reconstruction techniques. And I put this kind of approach in the family of point map regression, or T3OR, and you will see why I call it like this family. So some of you know about Duster, for instance. Does it ring a bell to some of you? That's very recent, so yeah, I don't see many hands being raised. So this is something we'll try to discover. So again, that's a bit ambitious. I hope we can cover everything. But before going into like those trendy techniques, let's first talk very briefly about the foundation of that field. Okay, like I think Shefali later will explain in more details, but I would like to give you a few basics that we'll need for the rest of that lecture. So I want to start talking first about photogrammetry, you know. And when we talk about 3D reconstruction, like many people are thinking, wow, that's something, that's a new technology, right? But if you look back into history, I think we need to be quite humble, because this field of photogrammetry, which is basically the field of science where you try to reconstruct the environment from a set of images, so this field has been funded in 1849 by Aimé Lozada, who was a colonel in the French army, and he was also passionate about mathematics and geometry. Okay? And at this time, already all the mathematic foundation to make 3D reconstruction existed, because people were doing a lot of mapping. Okay? That was something, a very strategic thing, actually. And also, Lozada was interested into another technology that was relatively new, that came 20 years before. It was the invention of photography by Nicéphore Niepce. And he was like, hey, why not combining those two things together? Okay, like we take images, and then, well, if I know the position of that point in that image and the position on this other point in the other image, maybe I can do things with that. I can do some mapping, okay? And after that, the Germans, they were very interested into that, and they actually expand the field quite a lot. And I have to say that after that, we haven't invented much, like all the foundation, like all the mathematics behind 3D reconstruction, they were known at this time, okay? The only thing we have done in the past centuries is like basically making it faster, automatic, more robust, denser, those kind of things, okay? And how we did it is basically, so here is the magic of that, I will say, or the core of this. Like if you have a set of multiple images, and if you're able to find strong and good correspondences between key points in those images, then you have done 99% of the job. Okay? If you have a set of images with correspondences between them, the rest is merely just a bit of linear algebra and nonlinear optimization. Okay? If you have good set of correspondence, the problem is resolved. Okay? And this is where a computer are very interesting, is that we can automatize that process. And before Lozada, the guy was talking about, like he had to do it manually somehow. So you can see at the bottom here is the pipeline of Colmap, which is a very well-known pipeline for 3D reconstruction. This is open source. I encourage all of you interested in 3D to try to make your own reconstruction, okay, using this pipeline. And you can see this green rectangle here is basically everything about image matching. And you can see it's the very first step to basically 3D reconstruction. So if you do it right, the rest is basically just some estimation and optimization, okay? So I will try, so if you do it right in photogrammetry, here is the kind of result you should obtain, okay? This one is a particularly good kind of result, actually. This is unlikely if you run Colmap out of the box, you will get such kind of representation. So now I will try to briefly describe the different steps you need to go through if you want to actually obtain those kind of results, or at least the foundation of it. So the first thing that you need is, of course, to collect the data. And for this, you can collect it in the way you want. You can take UAVs and you can reconstruct that school, for instance. Or you can, like, more trivially use your cell phone and, have fun taking your picture. You put this into Colmap and you will get your reconstruction. Or if you're a professor, like my friend in Sofia Antipolis, is that, he built this helmet full of GoPros. He took a random student. He's okay, now you will, like, roam around the city and we'll reconstruct it. So, and I find personally that, like, you might think that this is a simple thing to do. Like, I take a couple of pictures, I feed like whatever pipeline I have, and then it's gonna work. I will get my 3D reconstruction. But in reality, just this first step is actually not as easy as you think. And that's the reason why I encourage you to get your hands dirty. And you will realize quickly that you have to be careful of so many things. And here is very non-exhaustive. You should avoid motion blur. You should recalibrate your camera. You have to make sure you have enough overlapping between all of those images. Ideally, you should maintain some consistent lighting. You should avoid having like some rolling shutter effect. So many things that can go wrong just at this stage, okay? And so this is, the input. And as you know, like we talk a lot about that in this summer school, is that if the input for any learning pipeline is wrong, then the output is going to be bad, right? So this is the same here in 3D reconstruction. The next thing you will need is to understand and to be able to model basically your sensor. So you want basically a model that can represent this projection between the 3D space and your 2D sensor. Because this is exactly what is happening when you take a picture. Like when you press the button on your camera, what is happening is that you project our 3D world onto a 2D surface. Okay? And you need to mathematically be able to model that thing. And in computer vision, we like to make things easy. So like the way we model that is using the pinhole camera model, okay, which basically can express this projection on your image plane like through what we call the intrinsic parameter, this 3x3 matrix. So I'm not going to go through details on that, but I will explain you why this is important in the next slide. And one parameter you might already be familiar with is the focal length of your camera. Okay, how much you zoom, basically. Okay. And to get those parameters, the first thing you will have to do is to calibrate your sensor. So you will have to take multiple images of a known 3D object and do some calculation that Shefali will explain later, actually, and you can get back to your intrinsic parameter, to the internal geometry of your camera. And why is it so important is because it gives us quite a lot of information about how the image has been formed, okay? Like if we take basically a random 2D coordinate point on that image, let's say this point P1 in that image, if you know the intrinsic matrix called K1 here, if you multiply the 2D coordinate of this point by the inverse of this matrix, so what you will get is basically you will know the direction of the ray of light that formed that pixel, that hit that pixel, okay? So you don't know the distance of that point because, like this information is lost in your projection. But nonetheless, you know something very important. You know, like, from what direction this light was from, okay? And why is it so important is because imagine now you have two images of the same scene, okay? And let's assume we know the pose between those images. You know the orientation and translation between those images. And if you know the correspondence of that point in the other image, then you can also basically draw this ray of light. And the intersection of those two rays of light, this is the magical thing, is that you go back to the 3D structure. You know where this 3D point is located in space. So we started from 2D images, and now we're back in 3D. And that's the reason why this is so important to have the intrinsic parameter, okay? So you see that, however, you need to know the correspondence between those 2 points. And how we do that, so in general here, I'm essentializing a bit. That's a bit more complex than this, but you will basically detect some interesting point on the left image. Maybe you cannot see them well. There are red points here. So some point of interest for the left image, and you will detect some also in the right image. Okay, that appears in green here, but again, I will share the slide, you will see better. And then we'll extract patches around those key points, and we will extract some representative descriptor out of them. So it can be done with a neural network, it can be done using the gradients of that area, whatever, okay? And then we can compare them and basically match them one with another, okay? So this is basically what we do for feature matching. And if your matching is good enough, and if you're lucky to have at least 5 points in correspondence, then you can basically estimate jointly the pose between your cameras, so this rotation translation, and also the structure of the scene, this tiny 3D point cloud here, okay? And now that you can do that, you can start to aggregate more images to a reconstruction. So you start from 2 images, and we do what I described right before. We triangulate a small set of 3D points from those 2 images. And if you want your 3D reconstruction to grow, you will simply match a new image with those previous images in your map, and then you will get some 2D, 3D correspondences, and you can localize this image. And now that you know the pose of that new image, you can triangulate new points. So you add those points to your 3D reconstruction. And you keep doing that again and again, and you repeat that process, okay? And when you're done with that, in general, we run a global nonlinear optimization on it that we call a bundle adjustment, where we'll try to improve the quality of the poses and the quality of your 3D reconstruction such that the reprojection error is minimized. Okay, so just something to make it better, to make it like more global. Okay, and this is the kind of result we obtain in the end. Okay, what do you think about that? Is it a useful sort of like reconstruction? So I see many people saying yes, and indeed there are so many useful things, and we'll reuse them later. Okay, like here, so the process I have described briefly is what we call structure from motion. Okay, and we get like 2 interesting things. First, we have the exact pose of all those cameras, and in general, using structure from motion, this is pretty accurate. And we also get a reconstruction of the scene, but you see that this is not exactly like what I advertised to you first, okay? It's not a dense reconstruction. Sometimes for a human, it's a bit difficult to understand what we're looking at, you know? This is a sparse reconstruction of just a few 3D points, okay? And in general, in photogrammetry, we would like to have those kind of final results, like something dense and beautiful, you know, that makes more sense to us humans, right? So how do we get this? In general, we have one more stage after this structure from motion process. we have basically what we call multi-view stereo. I'm not going to go through the details of it too much at this point, but this is basically how you can densify your reconstruction. So for each image that you have, we try to obtain a dense depth map that we'll use to basically mesh our final reconstruction. So, and you should end up with something like this, okay? Here it's a video I took from a company called Mosaic, and they do a fantastic job. What do you think about that reconstruction? It's amazing? That's good, but like, okay, show that to your mom, and like, do you think she will believe this is, you know, like a real video that you took from UAV or whatever? This is obviously fake, right? We can see things floating around. When you have reflective surfaces, this is completely wrong. There are like plenty of artifacts. You know, this is not photorealistic, and those kind of strategy, they will fail if the surfaces we look at, they are not Lambertian. I don't know if we'll see an example of that, but if you have windows, like it's likely the reconstruction won't look good. We won't simulate like the reflection on the cars. If there is like, for instance, fog as well, this is not gonna work very well. And you see like the thin structure, they're gone, okay? So there are a certain number of limitations to photogrammetry. Again, that's a fantastic strategy, but you will never end up with something photorealistic. And this is where deep learning per scene fitting are coming into action, actually. And we'll start talking by the most famous of them. Some people know about what is NRF, neural radiance field. I think a few, yeah, I know you know. So yeah, some of you already know this, and I will try to briefly describe actually what is neural radiance field, okay? And so neural radiance field is, so all these nerve things are basically a strategy to create some synthetic view from some, so you have some training data, you have some views of the scene, and using this view, you will try somehow to encapsulate your 3D scene inside of a neural network from which you can generate as many synthetic views from any viewpoint you want, okay? And those kind of strategy emerged in 2020 in a paper published in ECCV that is entitled Representing Scenes as Neural Radiance Fields for View Synthesis. And frankly speaking, I think this is the most exciting paper I have been reading for the past 10 years at least. And even if you're not very interested into 3D, I think there are so many things to learn from that work actually. And I encourage all of you to have a look at this paper. There are many things that are intriguing, I would say. So in NERF, you know, unlike what we have seen before in photogrammetry, like that's basically photogrammetry is using what we call explicit representation, okay? Like something very tangible that will express the 3D structure of the scene directly. For instance, 3D point cloud or mesh or depth map or like voxel representation. There are things that even if you look at them, you can understand what you're looking at. You can see like what object we're looking at. So they're explicit representation. NERF is actually doing the things quite differently. It's using something that we call implicit representation. So this is a way we can represent the 3D geometry of a scene, but not in a direct way, you know? And it's not actually a new thing. There are already like some strategy to implicitly represent the 3D structure of a scene. Okay, like for instance, a well-known one is the sign distance function. Instead of representing your scene using point cloud, for instance, we can have a function that will describe your scene, and any sample in your volume will basically have a value. It will be its distance to the closest surface. That will be positive if it's outside of the shape, and negative if it's inside. Okay, so here we just have like a function to represent the things. In practice, like we have a discretized version of it, so a voxelized version of it. And so those implicit representations, they look rather complex, and you might wonder like, why we want not to express directly the 3D structure of the scene, why we want to use those things. The thing is that those implicit representations, they tend to have a certain number of properties that are very interesting. And you know, in this winter school, you have studied about like all those neural networks, and one thing important in neural network to work is to be differentiable. And one of the advantages of those implicit representations is that they're often continuous and differentiable. Even though for SDF, we tend to voxelize this thing, to discretize it. And, you know, all implicit representation, they are not born equal, okay? And SDF, for instance, is a great thing that has been used for a long time, but this is not enough for many kind of application. It takes a lot of memory, and also, as for photogrammetry, it assumes Lambert surfaces. So it means that you cannot represent reflective surface or fog or like those kind of things. Okay? And this is where NeRF comes into play. Okay? NeRF is basically an implicit representation where you will try to learn your scene and store it in a neural network. Your neural network will become a sort of memory, okay, of what your scene should look like, and from which you can generate new views out of it. Okay, so if you look at those two videos here, I will try to come back to it. So you can see the picture that we have here, they are not pictures that we have used to make the 3D reconstruction. They are actually new picture generated by a neural network that has somehow understood and remembered your scene. And the difference with photogrammetry that we discussed before is that you see that we can see all those sharp, tiny details in the object. Here we have like all the reflections that are like perfectly reconstructed. And all of this is learned like in your neural network because it has this flexibility. And this is something very difficult if you want to encrypt those kind of things. So at this point you might wonder, how are we gonna do that? How a network can like store that thing? So before starting talking about 3D, let's think about first about an image. Let's think about 2D. Like for instance, how can you have an implicit representation of an image? Or saying differently, like do you think we can store that picture inside of a neural network? And whenever you want to get back this image, you know, you can spit it out. Okay? It's a form of compression, if you prefer. Okay? So how can we do that? Do you have any idea actually of some architecture that can potentially do that? So maybe some of you might think about autoencoder, but let's think about this kind of structure, okay? Like here you have a small image, that's a tiny French flag of 4 by 6, okay? And you can see that each pixel in that image has an XY coordinate, right? So what if we create a small MLP? So you know MLP, we discussed a lot about that in this summer school. You have this small MLP, and then the input will be the XY coordinate of a pixel in your image, okay? And you want the network to spit out, to tell you, oh, what should be the color of that pixel? So for instance, we take the pixel 0, 0, it's our input, and you want your network to learn that the output should be 0, 0, 255, for instance. It's a blue pixel, all right? And you train it many times. You say, hey, remember this, all right? So you will do many iterations such that it will remember. And you will do the same for every other pixel in the image. Like, for instance, the pixel at position 1, 3, it's a white pixel. Everything is 1 or everything is 255, okay? So now big question is that, is it gonna work? Who thinks it's gonna work? Can you raise your hand? Nobody thinks it's gonna work. Because like for me, like if you ask me that thing, like 5 or 6 years ago, I will tell you, of course it's gonna work. Why wouldn't it work? That's a very simple problem, you know? But in reality, this is absolutely not working, okay? Like you can see that here is the image we want to store in our neural network, and on the left-hand side is what the network has learned, okay? Like we try to ask the network, okay, what is the color for each pixel of that image? And you see he's not able to solve our problem. He loses like every tiny details in that image. You see that we somehow have like a rough idea of how it looks like, but all the high frequency details are gone. The texture cannot be represented. And why is that? Is because inherently, MLPs, they favor like low frequency pattern, okay? And there is something that also you guys have talked a lot about during this summer school is that we can use positional encoding to resolve that problem. You know, something used in NLP originally, okay, to know what is the position of your token for instance, a transformer network. Here it's exactly the same principle, is that instead of just using the XY coordinate as input, we'll somehow artificially lift the dimensionality of the input by using some sinusoidal transformation. So instead of just the X value, we will apply like plenty of sinusoidal function to it. And what you will end up with is instead of using the XY coordinate, you will just have some additional module called positional encodings that will give you like much more input than before, okay? And just changing this, you will be able to capture all the tiny details of that image. Now this is what your network has remembered about your 2D image. Okay, so now you know that this is possible to basically use your network to have an implicit representation of a 2D image somehow, like, or a compression somehow of a 2D image, and like you can basically get this image back out of it. Now we want somehow to do the same thing about 3D. And then at this point you might think, hey, that was rather simple for a 2D image. You know what, let's just make the same network, we'll just add one new input Z, and we're done. Okay, intuitively that's what you may think, but it's not gonna work like this, because the problem we're trying to resolve is that we don't know the 3D structure of the scene in the first place. We start with a set of images, okay, and we want to basically have an idea about this 3D scene. Something here that is fundamentally different than just a 2D image is that in a 3D scene that you reconstruct, almost everything in your scene is just emptiness, okay? The only thing we care about in 3D reconstruction is the surfaces of the thing that is surrounding us. But you know, like the thin air here, we don't care, right? So this is also something we'll have to consider. This is extremely sparse, okay? So also we want to take care of things that were not existent in 2D images. We want to be able to represent transparent and reflective surfaces. So the problem is actually much more complicated. And to understand how we can address that, I propose you to go back in time, like back in actually the mid 80s. Like I think I should have put the reference, I forgot this. So in the mid 80s, like some people were interested about something called volume rendering. And the principle here was not to make 3D reconstruction, is that we assume that we already have a 3D reconstruction. We have some volume of our scene. So if it simplifies your understanding, you can assume, for instance, this is a data structure that contains the information of the scene. You can consider its voxels, for instance. Later we'll see how to do it with a neural network. And so in this volume, you can sample any XYZ points, okay, in that volume. You can say, hey, for any XYZ point in that volume, I want to basically get the color of that point, okay, exactly the same as in our 2D image in the end, but now we have something else. We also have the color and the density at that XYZ point, okay? And basically if you sample a point, for instance, where my pointer is looking at here, you see that here this is empty in that location. So in that case, the density will be 0, okay, because there is nothing interesting, there is no surface, okay? And if you try to sample a point that belongs exactly on the surface of an object, it will tell you, oh well, at this XYZ location, this point is, I don't know, yellow, and it has a density of 1, because this is an opaque surface. Now if you sample a point on a transparent surface, probably you will have a density, for instance, of 0.5 or something like this, okay? So you can also have those, you know, transparency implicitly somehow represented by this density value. So now the point of volume rendering is like to generate images out of that volume. So you can think, for instance, for video game is very convenient, right? So you can say, oh, why? You know what? I want to generate a 2D image as if it was acquired by a certain given viewpoint. I say, okay, I put my camera in space at certain rotation, translation, and I'm like, okay, now how my image would look like if I was taking it from that location. And what you can do to reconstruct this image is basically you can, for each pixel in your image, you can shoot a ray of light. And how do you know this ray of light? Well, like the intrinsic parameter of your camera, remember that, okay? So you have this ray of light in space, and what you can do is sample tons of points along this ray of light. And now you will want to integrate as many samples as you can along that ray to reconstruct what color is that pixel, okay? So you see the equation at the bottom here is basically a discretized version of this integration, okay? So like through many samples, we want to accumulate them to reconstruct the color C for this ray of light R, basically, okay? And let's see a bit more in details because, well, it sounds rather simple to do that, but this is actually more complicated than it seems, okay? So imagine we have a camera located at a position RT, and we want to know the color of this pixel P, okay? And in our 3D volume, we have those two opaque surfaces. We have this blue one and this purple one. Okay, so now we know the position of our camera, we know our intrinsic parameter, so we can shoot this ray, boom, okay? Good. And you can see that this ray is intersecting those two surfaces. So what should be the color of that pixel? Should it be like purple? Should it be blue? Should it be both of them? Yeah, I hear many people saying blue. Yeah, indeed. And why it should be blue is because it's basically, you know, this surface I told you is opaque, it's not transparent, okay? So it means that this one in the back is completely occluded, okay? So you want to make sure that you won't also accumulate points in that surface. And that's the reason why, like, this equation is actually more complicated than it seems. Let's see what is inside of this alpha I here. And, okay, yeah, of course we have to sample many points along this ray, okay? And for each of these points, we will basically take their color and the density at this location, okay? And now it's how this equation looks like, okay? So, well, it looks a bit more messy now. And you can see that actually all this part, this alpha, is what we call the visibility, okay? So there are two parts in that equation. Like the right-hand side here, the 1 minus exponential of minus density multiplied by this delta, and delta is simply the distance between successive sample. This guy here, this parenthesis, is to say, okay, I look at this, at a sample individually, and it's like, should I consider this sample? Okay, because basically, if your sample has a density of 0, so exponential of 0 is going to get you 1, right? And then 1 minus 1 is going to be 0. And what will happen in that equation is that if you have 0 density, you need to omit this sample. Okay, this sample is useless somehow. Okay, it's representing emptiness. So, and if the density is high, for instance, if the density is 1, we have exponential minus 1, or minus something high, okay? Then you will get, yeah, it will be 1 actually. Then you will get 1 minus 0. So potentially, like, this part will be like, okay, we need to consider that sample because it has a certain density. So it means that this is a surface, okay? And this over Ti here is basically how you will consider, like, occlusions in your scenes. It will consider all the previous samples you have visited, and it will see if this ray of light hasn't been already saturated, meaning that if I am basically treating some part of the scene that are occluded by something else, I don't want to integrate it in my pixel color, okay? So we can see a step-by-step description of this. So we can see, so here I call the right side of this equation beta I, okay? And let's see, like, the value Ti and beta I for each of those samples. So for the first sample, basically Ti will be equal to 1, because here you see that we are in an empty place. There is no surface at this location, right? So Ti will be equal to 1. So beta 1 will be equal to 0, because so far we haven't visited yet any previous samples, okay? And then we'll, move to the next sample, okay? So here we're still in the emptiness, so Ti will be 0, beta 1 will also be 0. The next one will be more interesting because now we will be very close to a surface, okay? So we'll have a density that won't be equal to 0 anymore, okay? So if the density is not equal to 0, it means that this value here will not be like 0, it won't be equal to 1. It will be equal to 1, and Ti, in that case, will actually, so before we had some empty space, and now we basically, so beta will become equal to 1. So it means that here, you see that this left-hand side won't be equal to 0, which means that we'll consider that color to be integrated, okay? And after, we'll move, like, further than the surface, and so all of a sudden, like, okay, we're still in empty space here, so T will be equal to 0 and beta equal to 0, etc., etc. And even if we meet another surface later, actually what will happen is that we won't consider this surface anymore because T will remain equal to 0, okay? So I messed up some stuff. The slide is correct, but when I say it was messed up. But anyway, so T will remain 0 as soon as you meet the surface. You can see before meeting some high density, T will be equal to 1 and it will be equal to 0 all the rest of the time along this ray. Okay, so that's the global idea, I would say. So this rendering equation that again has been developed in the mid-80s has very cool property when it comes to neural network. Is that now this equation is fully differentiable. And the goal of NERF, actually, instead of just, like this need to reconstruct image out of your volume, now is the inverse, is I will give images, and I want to learn this volume. And what do you need to learn in your volume is that for every point in space, you want to know the density of this point, and you want to know the color of this point. And now how we are gonna learn that is we'll try to store this information in a neural network in the same exact fashion as we were doing for a 2D image. So now your input will be the 3D coordinate in space, and the output will be the color and the density. And this network is nothing but just a tiny MLP, okay? And you can see that now we have also two additional parameters, which are actually two angles, and you might be like, what the hell is this now? Why we need that thing, okay? And it's for a simple reason, is that depending from what viewpoint you look at a surface in space, for instance, here is some picture I took from a table, okay? You can see that in this green square, it's exactly the same location on the table, but if you look at those two patches, they look different, okay? And they look different because they reflect the light differently because I look from a different viewpoint. And this is what those additional two inputs are representing, basically, okay? Is to say, oh, well, I'm looking at this point in space, but I'm looking at this point from what viewpoint, okay? And now the network can also learn about that. So this is actually something that is not entirely required if you don't care about reflection, but you will lose some important information. It won't look photorealistic if you omit those parameters. You will get something that probably won't be that good. So that's exactly what NERF is doing. So we start from a set of images, we sample point for every pixel, for every images in your data set, and we want basically the network to learn how this point in space, what is their color and density, such that you can reconstruct the image accurately. And to train that, you will basically try to minimize the photometric loss, the difference between the image that you reconstructed and the image you use for the training. So somehow you want to overfit a network to learn that scene. And how you can do that? So first you need to know the poses very accurately for each of your camera you want to use to make this 3D reconstruction. And how we get that? Well, good old structure from motion, what we have described before. What Shefali also, I think she will give you some more intuition about that, okay? And how we train this, I already mentioned it, is that we try to minimize the discrepancy, we try to minimize the error between the training image and the reconstruction that you render out of the volume you're learning, okay? So now you might be wondering, how do I select those samples in space for each of the rays coming out of my training image? So, and this is actually a very central problem in NERF. So one simple way to do that, intuitive fashion, I will say, this is simply you divide your volume into equal distance size, and for each of those cells, you're gonna basically randomly pick a point, and that's gonna be one of your sample along this ray, okay? And well, potentially this thing can work, but you will need a lot of samples. And you see that here, we treat all the samples as if they're equal. But in reality, I told you that we have mostly everything is emptiness. But what we care about, this is where the surface exists. And that's the reason why actually one of the contribution in NERF as well is like how they do this sampling is in the hierarchical manner. So first they will apply the strategy that is described here, uniform sampling, all along the ray of light. And this is what we call a coarse sampling. And from this coarse sampling, we can basically have an idea about the density along this ray. So a very coarse idea, something not very accurate. But now what we can do is we can have a resampling near the potential surface in your scene, okay? And you can get basically a much finer reconstruction by doing that. And now the final loss we use, the previous one I showed you was a bit wrong, because I tried to simplify it. But a loss that is often used is that basically the combined loss of the coarse reconstruction and the fine reconstruction as well, okay? So also something that is maybe just a technical detail in the end, but anyway, actually a NERF is composed not of a single network, but of two networks. You have one that will only be here to, so you give the position x, y, z, and it will only provide the density at that point, okay? And also a feature vector that will be passed to another tiny MLP that will also consider the viewpoint, the orientation that we were talking about before. Okay? And then it will give the color. And why is that? Is because actually the density, it has nothing to do with the orientation. So by separating those two tasks, we can basically deambiguate certain potential problems that you might face. Okay? Okay, also don't forget to add the positional encoding, because in 3D is the same problem as in 2D. If you don't add the positional encoding, you will get a reconstruction, but that will be all very fuzzy. Okay, it's not going to be very accurate. So you need to add this positional encoding as well in your input for the 3D points and the input for the viewing orientation. Okay? And in the end, if you train your network properly, you should end up with those kind of images. Okay? All those images, again, they're obtained by the neural network itself. Okay? So they're not images that have been acquired during the training time. So here is a few examples with real images. So you can see that we can synthesize as many images of the scene as we want. Okay? And implicitly, all the 3D information about your scene is inside of the network. And eventually, you can get it back if you want. Okay? So this work was like basically the first of like so many follow-ups work. So because there are still a lot of challenges that were remaining, you know, after it came out, and people were very excited. So the evolution of NeRF was so fast. Okay, like in a couple of months, even like some very interesting paper came out. So one of the premises, for instance, how you can apply NeRF in the wild. So in a very complex setup where each camera has different parameters, each image has been acquired under different illumination, etc. You have also like how we can make them faster. Okay, like this is, for instance, what NVIDIA tried to do with instant NGP. How, if our camera, they're not calibrated, can we still do that? Okay, those kind of things. And there is still much more to explore. And I think like NeRF, they're fantastic. But they still suffer quite a few limitations. So first, this is very difficult to represent some large scenes with NeRF. Okay? You might have many problems. You might have the problem of catastrophic forgetting. You might have the problem on how can I sample arrays in a large volume. That's complicated. So actually, some people try to address this by decomposing the problem into like smaller NeRFs. This is what block NeRF is doing here. But overall, the problem of NeRF is mostly that this is extremely slow to render and to train. At least the vanilla NeRF is like extremely slow. It could take days, like back in the day, to train a NeRF, like at least many hours, okay, for a single scene. Okay, so nowadays there are plenty of new papers that you can make it much faster, but still it's a big problem. And why it's the case is because during the training or during the rendering, then what we have to do is that for every pixel in your image that you want to render, you need to sample and to query your network many times, okay? And you see that we waste so much time because most of the sample, I told you that in 3D, the only thing we care about is the surface of the object. The rest is nothing, okay? So you see that we're wasting so much time and energy sampling from useless location, okay? And this is one of the main reasons why NeRF is so ineffective. And this is exactly where Gaussian splat came into action. And so Gaussian splat is a bit of a more recent paper that came out in 2023, but it made already like a lot of children somehow. Okay, so this is also, so the idea of Gaussian splat, I will describe it to you in a minute, but here is the paper and reference. Also, I encourage you to look at this paper, even though I think this is a bit more complex to go through than NeRF, for instance. This is a paper that is very technical, and I appreciate it a bit less than the NeRF paper, but still the foundation of something very essential. And when they came out with their results, like, so it was a friend of mine from computer graphics that told me, hey, have you seen that paper? And I was like, okay, I'm not interested into computer graphics, but it ended up being like, actually, you know, even NeRF is very inspired by computer graphics, actually. And that's fantastic to see like the convergence of those two fields. And so he told me, yeah, this is doing the same as NeRF, but this is much better. And then he sent me exactly those graphs here, okay? And then on the left-hand side, you have basically some curves that are representative of the quality of your reconstruction, okay? And, well, they were extremely competitive with like the top NeRF at the time. And I was, okay, yeah, well, that's not that great, actually. That's just as good as NeRF. And then you look at the right-hand side, and now you see that the training time and the rendering time of this thing is much, much, much faster than nerves, okay? So you have similar quality, but much faster. So of course I was like, what is this black magic? Okay, and yeah, this is a lot of black magic behind this, a lot of tricks, you know, but quite fascinating. So the key idea here is instead of, you know, like representing the entire scene, every single point in your volume, in your space, the only thing we care about, I told you, is the surfaces. And then now it's a different way to represent surfaces. And we want to represent like everything that has a non-zero density, okay? So how we do that? We just put some blobs in space. And those blobs, ideally, they will be like around the surface of your objects, okay? And each of those blobs, now they will contain the same information as in the nerve. They will contain the color of the surface, and they will contain also the density of that surface. So basically, if you have a sample far away from all those 3D Gaussians in space, so here I draw them in 2D because it's a pain to make it in 3D. But basically, if you sample a point very far away from them, the density will be equal to 0. It's a useless point somehow, okay? And if you sample something closer to one of those 3D Gaussian, it will have a certain density and also the color associated to it. So here, it's a green blob, okay, that is floating in space. And we're not exactly in the center. So we can say the density is quite high, but maybe, you know, maybe it's a bit transparent somehow, okay? And if you sample in the highest density, then you will have a higher density, maybe 1, okay? And you will have some, you know, maybe a different color associated to it, okay? So each of those 3D blobs, which are basically 3D Gaussian, they can be quite beautifully expressed mathematically. So they will contain a certain number of information, like their opacity that we're talking about, the density, okay? How transparent my blob will be somehow. It will contain its color, okay? Exactly same as for, so each blob individually we will have its own color. It will have a center point. It's actually the mean of the distribution of your 3D Gaussian. And it will have a covariance matrix that will somehow encode the orientation, okay, of your blob, and also its scale along the different axes. So it's going to be a 3x3 matrix. And then, if you want to know the density at a point P, then you can simply use this equation here at the bottom. Okay, like if you know the position in space, the mu is the center, okay, and basically the covariance of that blob, the density at the point P in 3D space will be provided by this equation. Okay, so a 3D scene in Gaussian splatting will look like this on the right-hand side. So this is, I don't know if you can see very well from far away, but this is a bunch of like blobs in space, okay? And now you might be wondering how the hell we're gonna render that now, okay? And you know, like that's not as intuitive as we may think. So one idea we may have is like, you know what? What we can do is the same as in nerve. We have those blobs in space, and we can sample through each ray in my image, and then, you know, I do the integration in the same fashion. And, well, actually, it should work pretty well to do that. I don't see any reason why it wouldn't work. But then we end up with exactly the same kind of problem we had in nerve. We had to sample again to all those empty locations. And that's not what we want to do. But the cool thing with those blobs is that they have very fun properties, is that they can be projected onto your image, okay? So instead of doing like this integration, instead of doing that, we can just like somehow project them on your image. And this is why we call it a splat, okay? It's like you take your blob and you throw it on your sensor surface, okay? And to do that, so just for the centroid of your blob is very simple. It's just like a projection equation. You take your projection matrix and you try to project the center of this 3D blob onto your image. For the covariance projection, that will basically give you a sort of 2D ellipse on your image. So it's like, again, like if you splat it on your image, then it's a bit more complicated. I won't go through all the details of that. But this is from a paper called Iwa's splatting that came out a long time ago, more than 20 years ago, actually. And they figure out that it's actually a complex problem, but you can linearize it in some way. So you can see that here we can have a closed form solution to protect all those Gaussian in your image. So you don't need to sample. The only thing you need to do is that every Gaussian in front of my image I'm gonna like project them, I'm gonna splat them onto the surface of my image, and then I can blend them together, and I will hopefully get my image. So you see, like, you can basically estimate the 2D position of each blob in space. For instance, we take this 3D blob, and we'll try to project it on my 2D image. What I can do is, like, I can project its center and estimate its covariance matrix on my 2D image. And what I can do is, like, now, like, from this new sort of like 2D Gaussian in my image, for each point in my image, I can know what will be the density for that particular Gaussian. Okay? And then now, the beautiful thing, you don't need to integrate. You just need to project those guys in your image. Okay? And you just need, in the end, to blend them all together. So that's a bit more complicated than this, because first you need to sort them in order of appearance, from the closest to the furthest away, and then one by one you will basically blend them to get basically the color of your pixel until you have a saturation, okay? Until like, oh, you know that the density is too high and whatever is behind is useless anyway, okay? So no sampling anymore, fantastic, okay? In practice, if you read the paper, you will see that there are a lot of tricks to make it even faster. For instance, they work on 16 by 16 tiles to speed up basically the blending and the sorting, etc. So actually lots of technical details. So now there is a thing you might wonder about is that, all right, but what if I just have the positions of my cameras like in NERF, and how do I initialize my blobs? Okay. Should we throw blobs all over the place randomly and cross our finger that this thing is going to converge? Okay. And I will tell you, like, for a complex scene, it's not going to work at all. So instead of randomly initializing, they take advantage of something we have seen before. Okay. We'll take advantage of the prior structure from motion reconstruction. So you see that I talked to you about that. You know, it was not a coincidence. It's because now we need those guys. So each of those 3D points in space can be used to initialize our floating blobs Gaussian 3D in space, okay? So now they will be all very close to the surface, okay? So the problem is much simpler, and luckily maybe now we can converge to our proper reconstruction. So we start from a SFM 3-point cloud to initialize our 3D Gaussian, and we have basically our camera position in space, okay? And we'll try to basically project those Gaussian in the image, and we'll see how good it looks like. And what we want to do is to optimize those 3D Gaussian, meaning their position in space, their covariance, and their color, such that we maximize the quality of the photometric reconstruction, the quality of our representation of the 3D scene. So by placing those Gaussian in a better way, okay? And there are plenty of other tricks, okay? And I cannot tell you all, because that's you know, what I don't find very elegant with Gaussian splatting is you have a lot of tricks, a lot of hyperparameters as well. One important thing, for instance, is the pruning and spanning strategy. So, you know, some of the Gaussian, for instance, they will over-reconstruct, they will cover a too large space and you will lose details. And you need to identify those guys and to split it into like smaller Gaussians. And sometimes this is the opposite. You have a Gaussian that doesn't cover enough space, and then you will have to duplicate it. Okay, you will have to pop more Gaussians. So for every 100 iteration of your training or whatever number of iteration, then you want to basically check out, like, should I remove or add Gaussians in the scene? Okay, and if you do all this well, then you should end up with those kind of amazing reconstruction. So on the right-hand side is basically the Gaussian splatting, and on the left-hand side, this is like what was back in the day the state-of-the-art NERF. It was MIP NERF. Here they compare against much faster NERF rendering, instant NGP. And you can see that for something actually even faster, which is the Gaussian splat here on the right side, they get much better results, okay? So something very impressive. Still, there are so many challenges in Gaussian splat. I have a good friend of mine who made that video in France, in Sofia Antipolis, and you know, I'm a very bad friend because I forgot to put the reference. Okay, if you look for large-scale reconstruction, you will find it. Okay, it's the same group who made the original Gaussian splat paper, and his challenge is like how we can reconstruct a very big scene. So, you know, I told you, I showed you before the helmet with all those GoPros like all around, right? And this is what he did. So he had to decompose the premise also, like he's working with some octo tree. That's a rather complicated thing as well, full of tricks as well. And you know, I told you that this presentation will be about deep learning based reconstruction. And here you can see that I again lied to you a bit because there is no deep learning involved in Gaussian splat. Okay, which is nowadays quite surprising, right? But I see many people trying to put basically neural network inside. But you don't necessarily need it to make it work. However, like to train such kind of thing, we use basically the same training strategy as you might use for neural network. We can use like stochastic gradient descent or ADAM, for instance. Okay, so Gaussian splat, again, like really a revolution in like 3D reconstruction. You get photorealistic result in real time, super fast training, compact representation, very beautiful. But again, like the main problem to me is that you still need very strong assumption. You need first to run CallMap, for instance, or any 3D reconstruction, the street view from motion first, to get a prior sparse 3-point cloud and the poses, okay? And also like this reconstruction, they work per scene. So if you reconstruct this room, if you want to reconstruct the room next door, for instance, you need to start all over again. You take your picture, you put it into a SFM pipeline, and then you run your Gaussian splat, okay? So that's a bit of a pain. And there is something emerging this day that I find fascinating. This is the one-shot reconstruction. So here, basically, this is, you don't need SFM. You don't need to calibrate your camera. You don't need anything. You take 2 images of the scene, you give that to a big network, and boom, you get your beautiful 3D reconstruction. And it seems magical. This is magical as well. This thing is working much better than I would have anticipated. And all the research I will present today are actually from Naval Lab Europe in Grenoble. And actually, this part of the presentation is extremely inspired by a talk they gave recently. And I will try to tell you basically their story and like what was the path like they tried to pursue for the past 3 years. And I think they were doing fantastically well. So what they try to achieve actually is like they realized that in neural language processing, before large language model, like every task was, you know, like if you wanted to do reconstruction, you needed, if you wanted to do translation, we were like basically creating some artificial intelligence for translation. If we wanted to do optical character recognition, you need yet another network. You know, like we were creating specialized networks. So and since we have LLM, we see that this is working actually much better to have those big LLMs to solve all those tasks all at once, a unified model, you know? And this is exactly what they try to pursue for the past couple of years. Can we do the same as this revolution in NLP, but for vision, and more specifically for 3D vision, okay? And there are so many tasks in 3D vision. You can have like the task of depth estimation, relative camera pose estimation, visual localization, point matching, reconstruction we're talking about, and maybe much more. So can we have a network like that can solve all those problems all together, okay? And yeah, it seems quite ambitious, but I think they made it, okay? And they started by looking what existed at this time in 2D. And in 2D, we have seen that something that works extraordinarily well, this is self-supervised learning, okay? Maybe you know about Dino V2, mascot encoder, like, so we can basically, and we talk about, Binod made a fantastic introduction on self-supervised learning. Okay, but now the question is like, can we do the same but in 3D? And where they all started is with what they call Croco. Okay, and this is a self-supervised learning strategy for 3D. So let me just say a few words about, again, you know that now because Binod did the job very well. So self-supervised learning is a paradigm in machine learning where you train your model on a pretext task. So a task that looks useless, but you just do it because you can train it from the data itself. You don't need annotation, which means that you can train on so much images, okay? And this is something that, you know, Yann Lequin is almost always right, I have to say, okay? And a couple of years back, he said, okay, you know what we need to do, guys? This is self-supervised learning to give some sort of common sense, okay? Because like, for instance, us as a human, we don't learn just from pure example. We have like tons of context that we learn not necessarily to achieve a goal. but just from our surrounding. And that's what we want to do with self-supervised learning. We train a neural network on a useless task somehow, okay, such that he has some idea about this concept, and then we can fine-tune it for like a more complex or specific task, okay? And here are two different families of self-supervised learning techniques into the image, okay? Maybe you know some of them. So, for instance, contrastive learning is something that Binod briefly presented last time. You take a picture and you augment it in a certain fashion such that it will look different. You rotate it, you mess up with it. And you also take an image that has nothing to do with the positive samples. And what you will want to train is basically a network that will make those two similar samples closer to each other and the different sample further away in the latent space, okay? So here there are the contrastive techniques like Dino, for instance. And there are another kind of approach which are generative. So this one is, for instance, like mask autoencoder. You start from an image, you remove some part of that image and you try to in-paint it. You try to generate the missing part of that image. And if the network can do that, it means that it somehow understands some semantic about that image. Okay? So here is mask autoencoder. And Naver Labs, they were very, let's say, influenced by those work. And they wrote this paper called Croco, okay, that I recommend you to read. And the idea is quite simple, okay? It's like you take a pair of images, and the pretest task is that, okay, like you see in pair of images from the same scene. So you take a picture from that position, and you move, and you take the same scene from a slightly different angle, okay? And now, in the query view, you will randomly move some element in that view. You will mask it. And then now your network will have to reconstruct this missing part given the reference image. So do you think this network, I mean this strategy is a contrastive or generative approach? It's generative, yeah, because you have to generate a missing piece of the image. Very inspired by mask autoencoder. Okay, and why, you will tell me, why is it even related to 3D? We still work in 2D, but look, to do that, the network will have to implicitly learn about relative camera pose, image matching, depth estimation, prior shape about the 3D things you're looking at, colorimetric adjustment between the views, and et cetera, okay? And then their network really looks like mask autoencoder, except that now they have two VIT, like two networks, okay? That it's actually a Siamese network here. And they basically provide the encodings of both of those images to a decoder that will be used to reconstruct the image that you see that you have removed some patch from, okay? And they train this network using a ton of images, more than 7 million images, some are synthetic, some are reals, okay? And, well, here it's just, so basically, by pre-training their network with that strategy, like they try to fine-tune it for different 3D tasks, like depth map estimation, place recognition, whatever, okay, and as many tasks that they could. And they kill like most of the benchmark, just because they have a very good pre-training, okay? Here is example of reconstruction. So you can see the reference image on the top, and here is the mask image here. So you see they remove like 80, 90% of the image. You have almost nothing left, and your network has to reconstruct it, okay? So Croco is great, okay? But this is not what I sold to you before. It's not a unified model. This is just a pre-training. You still need to retrain for every task individually. And they were wondering how we can basically have a network that solves everything without any retraining, okay? And the trick that they found that is very interesting is that they try to create a network that can generate what we call, so this is a point map regression technique. So this is, what is a point map? Okay, you will ask me. This is basically, point map regression is like your neural network, its goal will be like, I give you an image, and the network has to generate 3 channels as output, X, Y, Z. So for each pixel in my image, I want to know the 3D location of this point in the 3D space in a given referential, okay? And then if you do this, it will directly give you something very, very important, is basically the 2D, 3D correspondences. And if you have the 2D, 3D correspondences, you can basically solve all the problem that I mentioned earlier, okay? And this is what they propose in Duster, okay, which is a paper that came out in 2024, so quite recent, okay? And they took their Croco base, okay, that's exactly the one we have seen in Croco, Okay? Except that now they have included a new head to this network, and for both images, those heads will basically try to predict a point cloud, or more exactly, like those scene coordinate points, okay, in a given referential, and actually in the referential of the camera number 1. And that's all they did, actually. And it seems simple, but the main difficulty is how you find all those data to train it, because now they're in a fully supervised setting, okay? So they needed data with poses and dense depth map as well, okay? But they figure out like where to find those. And actually, if you are able to have such kind of network, all those tasks, camera calibration, depth estimation, pixel correspondence, everything is basically resolved, okay? And it's on magic again, and it is. Like, here is a few results. It goes very beyond what you can think if you don't know Duster yet, actually. I don't know if okay, here is a video result. So you will see they took a picture of a teddy bear. They have one reference image, and they will basically use all the other image as the query image somehow, okay? So the first image remained the same, and the second image is changing all the time. And look, even when they're behind, when the camera, they look in completely opposite direction, they're able to know the pose very accurately and to reconstruct it. This is just, mind-blowing, okay? So Duster is working with 2 images, and, well, the generalization as well is, look at this. This is like what we call impossible matching. Like you don't have enough correspondence barely in those images, okay? And so, well, the result already is impressive, but like what they realize is that this is extremely robust, but in terms of accuracy, well, actually you can be better by, doing old school technique, point matching, etc., or different kind of neural network. They were like, come on, we want to push this further. And this is where they developed Master a few months ago, okay? And the only thing they have changed in Master, this is very close to Duster, but now they have one more head that will try to basically explicitly find some correspondences between images, okay? So I won't go through too much detail because the time has almost come, but they can also resolve some correspondence problem that were considered before almost impossible, okay? So from like very, very different viewpoints, they were able to still find correspondences. Here is like an example of reconstruction by using many images all together. And again, that's amazing. And I will let you look at the quantitative result by yourself, but yeah, they basically kill the benchmark for many, many things, especially in place localization. The conclusion of this talk now. So we have presented a couple of techniques. Some of them were one-shot, Duster and Master. So some, I talk a bit about photogrammetry and per scene reconstruction. And all those techniques, they have their own pros and cons, okay? Like I told you that those one-shot techniques, for me, they're extremely promising, I would say. But it doesn't mean they will work all the time. The problem when you rely exclusively on an end-to-end network is that if one day it doesn't work, if it's too much out of distribution, you will never know why. And there is no way you will make it work anyway, okay? So in terms of understandability, that's a bit complicated, okay? But it's quite fast. It's work on completely uncalibrated images, okay? If you feed those networks twice the same image, it's gonna give you the 3D reconstruction nonetheless. So this is even monoview, okay? So very, very promising, but again, I think there is still a lot of work to be done here. And the per scene reconstruction, what is beautiful about them is that they give you some very, very good photorealistic reconstruction, okay? Something very detailed that can consider reflection, et cetera, okay? So they all have their advantage and disadvantage. The main problem with per scene is that they, in general, need some very accurate priors, like the poses of your camera or the 3D point cloud. And they also, they are per scene training. So, like every time you face a new scene, you need to retrain something. And we can see like many new works coming out lately that try to combine actually those two strategies. It is the case, for instance, for Insta-Splat, where they take advantage of those Master and Duster to have a prior reconstruction, and then they will basically feed some Gaussian splatting to this reconstruction. And they can get like something without using structure from motion, so it's much, much faster, and they get actually pretty good results out of it. So you can actually try to combine them together. And that's what people are trying to do these days. Something very recent, like maybe last week or something, that is absolutely amazing is Master Slam that has been developed by the team of Andrew Davidson. And they basically take Master, okay, the one we were talking about before, and they basically, I didn't read the paper yet. I just saw the video. I was like, I need to put this into the slides. And they get real-time 3D reconstructions. All of this is real-time, dance, just by using this out-of-the-box network, okay, that works in an unknown environment. Okay, so it looks pretty cool. Again, like before I can be conclusive on that, I wish I will have time to read that work. But if you're interested, I encourage you to look at those new developments. It's very exciting. And what will come next? Well, I think there are still many challenges to be addressed. Okay, there are still many cases, and I think this is our role actually to see when those things are not working and what we can still like improve. Like, do we want to tackle more real-time something faster or work into a dynamic scene? Okay, there are plenty of things that can be explored. And the motto of my university is like history maker. And well, this is what I think we need to do is maybe to make history, at least in that field. And that's the last slide of this presentation. Thank you very much for your attention. And
do you have any questions? Can you please raise your hand?
Hello, Professor. This was an amazing session. So I don't know much about FFM or one-shot reconstruction, but I'm curious about how much fast is it from person reconstruction?
oh, you mean like for the SFM itself?
Yes.
It can be very long. It depends on the number of images, but to reconstruct that room, I will take a couple of hours. So this is, yeah, it's very slow. It's very slow because you have many processes. You need to detect points to match. Imagine you have 1,000 images, yeah, a couple of hours at least, more than this probably. It depends what computer you use, but yeah. You can do things on GPU parallelized, but this is still very computationally intensive. So this is a big problem indeed. Yeah.
And okay, so now I'm talking about the person reconstruction. I'm not in 3D person static. Is there any work for dynamic object because they assume the object must be static?
Yeah, there are plenty of works about that. So they have some results, but in general, this is still quite restricted, I believe. Like this is in a small scene, and like you might have some restriction about the motions, and you need often some additional prior about the motion. Like some people might use optical flow or depth, but there are many things going on actually, yeah, in that field. This is still an active field of research. There is still work to be done here to really make it. You know, that is going to converge, that is going to be compact as well, because now you have one more dimension, you have the time. So now imagine you try to fit a dynamic scene with splats, I mean with Gaussians. Then like, do you pop new Gaussians or do you try to move the Gaussian in space? You know, like all those things can take much more space, for instance.
Okay, so can I understand as the model is overfitted in one type of data set?
Oh, for nerve.
Yes.
That's exactly that, yeah. This is almost an overfitting, because we still want the model to somehow generalize a little bit such that you can generate some views in between, okay, like a bit far from your training set. But yeah, we can really, to simplify, we can really say it's an overfitting, yes.
Yes, for the Lego dataset, we don't overfit in that dataset and we generalize in that model. Can we using other dataset by generating pointers from full map? So how much fast will it be using RAW?
Oh, excuse me, I couldn't catch it. So
the question that I want to ask is, I generalized the model from Lego Dozer dataset, the one in the paper.
okay.
Lego Dozer.
Yes, I see exactly.
And I generalized that model into my new dataset.
Oh, well, you cannot do that because your network will have learned a scene already, right? So if you present a new scene, it will have to unlearn everything that he has learned before. I don't think pre-training will even help in that case that much. It's nothing I have never tried actually, but I'm not sure pre-training a nerve will be any helpful it will never generalize. This is not designed for it.
Okay, thank you.
My question is in 3D modeling, if we don't want to represent solid irrelevant parts or solid undesired part, can we do binary model accuracy? Are there any established technique for that?
Sorry, to remove some part of the reconstruction?
Yes.
Why would you like to remove some part, sorry?
If you want to represent something cultural heritage, we don't want to represent garbage or anything like that in model.
To represent somewhat, sorry?
Maybe like some important details that we don't want to be displayed. That's something important to the heritage, and we don't want it to be displayed.
Oh, well,
You want to avoid the structures or something not of your interest. There are salient parts in the scene that you want to reconstruct, not the rest.
okay, well, basically in Gaussian splatting, you can basically remove, I think for editing, this is a bit more convenient than NERF. I'm not sure if DP will agree with me, but because it's a bit more explicit, and probably you can like edit it in more easier way. I don't know, or you can mask part of your image, I guess. You just need to sample rays where you want to sample. Okay, if you have a mask of your image, you say, okay, I'm not gonna sample any rays on things I want to mask. And you're basically gonna reconstruct only what is of your interest. It's gonna work very well, I think.
Thank you, sir. I was working on a Gaussian splatting project a few months ago. So I wanted some suggestions during data collection. So I realized that during feature matching step in ColdMap, the textureless surfaces like walls and streets is very difficult to match features in those type of surfaces. Is there a different way other than ColdMap to extract features and match them?
So, well, here what you describe is indeed a very complex problem, and unfortunately, like, I don't know something that is really much better than ColdMap. Now you have GlowMap, but it's not going to help the matching, and you will still suffer. So, one thing you can do maybe is like, maybe if you have some wider field of view in your cameras, then you will maybe have more texture, and then you have more chance to match. That can be one solution. Yeah, but. There is no magic actually here, is that still you will suffer. You can try in ColdMap to use some deep learning based matching, but in general they don't work that great. Like even superpoint, etc. is not gonna save your day, I think. So unfortunately, yeah, I don't have much advices I can give you on that. Maybe reducing the baseline between the images, but then you will have more computation. Overfitting is good because overfitting means that you have learned your scene very well. However, in NERF, something we might consider overfitting is that, or even in Gaussian splat actually, is that you can reconstruct the scene very well, and imagine you want to generate a view from a completely different viewpoints. Then it will look disgusting. Okay, that's what you may call overfitting. So those kind of representation, they're very good for interpolating between different views. But when you go out of, like, you're too far away from your training data, then this is, in general, not very good. Can we call it a problem of overfitting? Maybe. And in that case, yes.
Thank you.
Thank you. Hey, hello, I'm Francois Rameau. I'm a professor at SUNY Korea and also adjunct faculty at NAMI. So it's a pleasure to be here for this ANAIS 2024 edition. It's a pleasure for me to be here first, to be able to teach all those motivated and interested students in that field, but also because as an adjunct faculty here, I supervise quite a few students in Nepal, and this is also an occasion to meet them in person. This is a different feeling than just like talking to them through Zoom weekly. So, but it's not the only reason for me to be here. Actually, I was also participating in the last year edition of this event, and it was with a lot of enthusiasm that I wanted to renew that experience. And this year it was also absolutely fantastic in terms of organization, but also looking at the panel of the other professors that were invited, they were really like among the top in our field. And not only it's good for the student, but just for myself, I'm really enjoying my time in this edition. Like I'm learning quite a lot from all the lecture we have, and I think I'm gonna stay until like actually the very last day. So there are also many other events like that are organized, like hackathons, and I'm actually very curious to see what the student will come out with this year. And again, that's not only that. We are quite lucky to have a fantastic weather here in Nepal, and the Nepali are also in general, it's very welcoming. So I have a great time here, and definitely, if I can join for the next edition, if I'm invited, then definitely I will come. So thank you.